Lesson 22, resistance and Ohm's law. We will be able to describe resistance and use it in Ohm's law. Today's fact is about Joseph Swan, who was born in October 31st, 1828. Given that we're talking about resistance, it's actually a perfect lesson to talk about Joseph Swan. He was he was an English physicist and chemist, and he produced an early electric light bulb. And he also invented dry photographic plate. So photographic plate used to have to be wet. You used to have to put the chemicals on it. He was one of the first people to make it dry. An important improvement on photography and a step towards the development of modern photographic film. A man named Thomas Edison, we all know Thomas Edison, stole the idea of a light bulb from Joseph Swan. He took Joseph Swan's idea and used Swan's initial findings and tinkered with them a bit, and stopped short of him being called a thief. Swan, however, did not like that Thomas Edison was taking all the credit for filling his pockets with money made from his invention, and took Edison to court for the patent infringement. The British court stood by their patent award for the light bulb to Swan. Edison lost the suit. I actually didn't know that. That's actually news to me. I always thought that, but yeah, that's really good. Obviously, Edison still won because he was the one that made millions because he profited off it and made a business making the light bulbs, even though it was Joseph Swan's invention. But like, still, he probably got some money from it. I actually think this is really an interesting thing because it's one of those ones where it's the gray area between a stolen invention. Because although Edison stole the idea, he did improve on it. And in fact, that's what he did. Edison actually stole a lot of ideas from different people. But the problem is that he always improved on them to make them his own. And so because of that, it's hard to say whether he was how much of it he stole and how much of it he made himself. This is why whenever you create something, if you use someone else's work, you should credit them and say, listen, and there's a big thing about copyrighted music and stuff in YouTube videos and Twitch and stuff like that you can look up. But it's a big sort of problem and issue that we could talk about. The main thing is just to sort of say is like, if you at least acknowledge the person whose ideas you're borrowing or using, then you're less likely to get in trouble. Not impossible, but less likely. Right. So resistance and Ohm's law. What did we do last time that led us up to this point? Last time we talked about two major ideas, current and voltage. The first one, conventional current, we based off this idea of charge. Charge is the amount of coulombs, is measured in coulombs, and an electron has a certain amount of them. If you get charge moving, then you've got yourself a current. Current is charge over time, Q over T, and it's measured in amperes. We talked about how if you've got a closed circuit or a broken circuit, then there is no current, there is no moving water. It's only once you open the tap or open the switch that you start to see a current flow. Same with the switch. Switch is closed, broken circuit. If the circuit's broken, then there is absolutely no current flowing. But once you switch the switch on, then you get a current. The current starts flowing. Which way does the current flow? So yeah, you also need to have a circuit. More that you can't just connect it, you need to make sure that there is a way that the positive and the negative of the battery are connected, or the power supply. We briefly talked about how the electrons actually don't move very far down a wire, and actually it's the charge that moves down the wire quickly. And then we finished up, we sort of talked about electron flow versus conventional current. Conventional current is the one that we're going to use, which comes out of the positive and goes into the negative, even though that's not the direction the electrons actually move. And then we kind of wrapped up by talking about voltage, which is the amount of energy the electrons have, how much push they have. So if you lift an apple above the ground and you let it go, it'll fall down. So it has energy when it's lifted in the air. if you lift up electrons away from protons like they do in a battery, then it also has energy. That energy is voltage. I didn't get you a copy of the slide down because it's a bit of an advanced idea, but sure. We then talked about how a battery, how the electrons want to get around the circuit, which is why when we switch it on, the light bulb switches on. And then that was it. So that was the voltage. So now we're going to look at the third idea with circuits, which is resistance. What is resistance? Resistance is a measure of the oppositions to electron flow. Obviously, electrons want to go from one side to the other side. But if you start putting in obstacles to make it, challenging for the electrons to get through, then, it's going to mean that less, the electron's going to have less energy by the end of the day. This is called resistance. The resistance is a measure of the opposition to electron flow. It's measured in ohms, and that has the symbol R. It was originally first discovered by George Ohm. Hey baby, would there be any resistance at you? Oh, favorite jokes that I love about that. But resistance in essence is one of the reasons why you can be in the same room as a PowerPoint and not get electrocuted, because even though there is electricity in that PowerPoint, the reason you don't get electrocuted is because the air is really good at resisting electricity. If you are if you look above you at the overhead power lines, you're not getting electrocuted because the resistance, even if you hold on to your charging cord, it's plugged. I'm touching right now the charging cord going into my laptop. I'm not getting electrocuted, even though I'm touching something which has electricity running through it. And that's because the electricity finds it very, very difficult to get through the plastic and rubber that is around the cord that I use. If I was using like a metal cord just plugged straight into the laptop, then I might find myself getting electrocuted. So that's why that's what resistance is. It's how much opposition there is. Now, so let's look at this as a picture. It's the opposition to flow. So if I've got this tank of water, which represents the battery, and I've got this pipe, which represents wiring, if I was to drop a rock into this tank, like so, and the rock was able to bounce around and get lodged into that tap, what would happen is the flow would decrease. And the reason the flow would decrease is because it's now a lot harder for the water to go down the pipe. And the reason the water is hard to go down the pipe is because it got stuck. Someone wants me to go back to the previous slide, which was what? This one? Yeah, I'll keep it up. So yeah, but I can keep talking about that idea anyway. Because that rock went down that pipe and got stuck, it meant that less water was able to flow. So it meant that the flow of the water was decreased. And you probably know that whenever you put a finger covering up a water spout, that the less water is going to get through. So that's what we refer to as resistance. And of course, the thing is that with electricity, that obviously we can't just put rocks in the middle of a wire. But what we can do, I'm going to move on now, is that you can't put rocks in the middle of a wire, but you can add components. For example, this is a component called a resistor, and a resistor is just an extra little hurdle that the electrons need to go over before they can get back to the battery. So it's an extra thing that's going to use energy. It's going to have, these electrons are going to lose some energy to the resistor. So that means they will lose less energy to the light bulb. This causes the light bulb to become a little bit dimmer. Guys, hold on. Sorry. I'm having two people here saying, sir, I couldn't copy down the slide. Two people have asked me this like straight after one another. Like I kept this slide up for a good, like this slide here. I've kept this slide up for a good, and I've tried to talk about it. This slide here, there's only like two things written on this slide. I went to the toilet. Well, if you went to the toilet, then unfortunately you missed out. You're gonna have to copy it down later on, or you can open up the PowerPoint. If you guys miss it, you can go to the PowerPoint. It's available on the Google Classroom. You can look it up, or you can watch the video after class. But I have to keep moving on. I can't just stay on this one slide for like the whole lesson. A lot of students here want to, I want to get through this lesson relatively quickly, because I don't want to be here waiting around forever, because I've got a fair couple of slides to go through. So yeah, ultimately the electrons can't spend as much energy going through the light bulb. So because of that, the light bulb gets a bit dimmer. Now, different things have different levels of resistance, okay? We've talked about different levels of voltage. High voltage means you've got stuff like electricity jumping out of the sky, and then high current means you've got high current means you've just got a large wire. So what about high resistance? There is two ways we can refer to levels of resistance. Materials with high resistance to electron flow is called an insulator. An example of an insulator is something like wood, air, plastic. Skin is a pretty good insulator. Trying to think of something else. Paper is a pretty good insulator. All of these, rubber is a good insulator. All these are good insulators. They stop electron flow. They make it hard for electricity to move through them. And they're called an insulator. If you think about the word insulation, insulation is also what they put in walls, and that stops the flow of heat getting out. So insulation means it stops the flow of something. In this case, it stops the flow of electricity. These are our rocks. Rocks are a pretty good insulator too. So is glass. Glass is a good insulator. These are the things that stop the flow of electricity. The opposite of an insulator is called a conductor. Conductors, of course, if you think about the music, the conductors allow for the music to be played, they allow for the flow of something. So that's what we're talking about. Good conductors are pretty much anything made of metal. Copper, gold, steel, aluminium, all of these, mercury, all of these are good conductors of electricity. Graphite is also a good conductor of electricity, but the other standard one is water. Water is a really good conductor of electricity. That's why you need to be careful around electronic devices near your bathtub. I will point out that the water has to be have some salt in it. If you actually manage to get 100% pure water, when I say, and I mean 100% pure water, it actually won't conduct electricity. But the second you put your hand in there, in that 100% pure water, all the salt and sweat and minerals on your hand will get into the water, making it salt water, which is extremely good at conducting. Salt water is a really good conductor of electricity. So those are the two differences. Insulator means that it stops electron flow, whereas conductors allow electrons to go through them. This is why when you have to be really careful with pool lights and like electronics in the pool, you can't really watch a TV while you're sitting in the pool, because if that TV falls in the pool, you won't be around for very long. Yeah. All right, I'm going to keep this up for about another 30 seconds longer, and then I'm going to change the slide. All right, here we go. We're going to keep going on and stuff. You might get asked in a test or just in some questions, what's a good example of resistance, and what's a good example of an insulator or conductor. So having a couple of that you can throw out easily is pretty useful. Anything that like surrounds a wire is a pretty good conductor, is a pretty good insulator. The reason we have insulators in the first place is, like, one is for safety. One of the reasons that we put plastic around a wire, one of the reasons is just for safety, because if we means that we can pick up a wire without getting the fear of getting electrocuted. Even if that wire is plugged in, we don't have to. Imagine if you had to switch off a electrical cable every time you wanted to touch it. The second reason as well is to control the path of electrons. If you had to be careful, it's like, oh, I can't run another I can run two cables right next to each other and not worry about the fact that these two might, I can actually control the path of electrons because they are insulated. But if they were touching, then I would have so many different, I have to be really careful about how I put paths. So that's why putting insulators around them is really important. Back in the day, back in the early 1850s, they actually used to not really use insulators. They used to just like have the wire coming straight out of the roof. And believe it or not, even they also used to, in the early 1850s, sometimes they would use paper as their insulator. And I said paper is a relatively good insulator, but you should also think about it. Paper is also incredibly flammable. So it's not a good thing to surround wires with paper. You might not get electrocuted, but if there's a spark, you've just given that thing like plenty of fuel to burn down the house. So yeah, just a little bit extra stuff there. So let's just now take all of our ideas of current, voltage, and resistance and combine them all into one idea. To do that, we're going to use the idea of a river, because what we're going to do very often is we're going to use a river and water pressure to be analogous, which means, linked to our understanding of electricity. If you think of a river, you can think of the current in the river is exactly the same as the current in an electric wire. It's the actual substances flowing through the wires of the circuit, the electrons. The current in a river are the actual water droplets moving down the river. Both of those are the same idea. If you have a lot of water droplets moving, then you have a very big river, then you would say this is a high current. If instead you have just a little trickle, then that would have very few electrons going down or very few water droplets going down. So that would be a low current. Now, voltage is the force that pushes through the circuit. that is, and in this picture it's gravity. That's what's pushing this water down this waterfall and also down this river. Just like in a river, it's going to be gravity that's going to be pushing all that water down. And in a circuit, it's voltage that pushes the electrons around the circuit. If electrons had their day, they probably wouldn't move anywhere. But because they're so attracted to the positive side of the battery, they will move through a circuit. And that attraction, that willingness to move, that's what the voltage is. The last is, of course, resistance. This is the friction that impedes the flow of the current. It's like rocks in a river. If you look at this, because there are all these rocks in this river, it makes it really difficult for the water to flow. And that's what, and it's resisting the flow. Just like how a resistor in a circuit will slow down the current and maybe even bring it to a stop. These three ideas can actually be brought together. They can actually be brought together into one formula. And we're actually going to talk about that formula now. That formula is known as Ohm's law. And it is the formula V equals IR, where voltage is equal to the current multiplied by the resistance. So this is Ohm's law. It's going to be probably the most important law that we talk about this term, because it's going to be a law that we're going to continue to refer back to. I'm going to give you guys a fraction second to copy this down. Obviously, don't copy down the YouTube link. That'd be stupid. But just copy down the start here. It's also got what those things are measured in: amps, volts, and ohms. Okay. Now, one second, just want to check something. Okay. So, I'm actually going to take some time now to talk about how these things are linked, because I actually think understanding how these things are linked is really, really important. And to do that, we're going to start with V equals IR. Now, let's just say you've got a battery, and that battery is hooked up to, let's say that battery can only supply 10 volts or something. I'm actually going to do this over here. The battery can only supply 10 volts. And I've got current and I've got resistance. Okay, so if it can only supply 10 volts, let's just say that my current is, let's just say my resistance is 1 ohm. If my resistance is 1 ohm, then I can make the current be 10. 1 times 10 is 10. So that means I've got 10 amps worth of current, 10 volts. Everything's happy. But let's just say over time, the wire gets worn down or something, and it just doesn't work as well. Maybe it just breaks a bit. And so the resistance goes up. Let's say the resistance doubles. Now the resistance is 2 ohms. Now I'm not going to change the voltage. I'm going to keep the voltage the same. And we're going to keep it attached to a 10-volt battery. But now the resistance is higher. So because the resistance is higher, it means that it's going to be less current. The current is not going to be able to flow as easily because there is more resistance. It's like that river, And all of a sudden, what I've done is I've taken that river and I've added a bunch of extra rocks to that river to make it harder. So that means that the current now is going to be lower. It's actually going to be 5 amps. So if you go 2 times 5, it's 10. I've doubled the resistance, but I've halved the current, and I've figured that out using V equals IR. What I think is important to understand here is the formula and the idea are linked. It's like, okay, if we make the resistance higher, then the current is going to go down. Less electricity is going to flow if you make the resistance higher. Let's make it even higher. Let's take our 10 volts, but instead we're going to use 4 ohms of resistance. So if I've got 4 ohms of resistance, then that means that current gets even smaller. It goes down to 2.5 amps. So 10 volts, 2.5 amps, and 4 ohms. So because it's so hard for the electricity to go through the circuit, the flow of the current is really low. You can even go as high as, say, 20 ohms worth of resistance. Now, if there's 20 ohms worth of resistance, your current is going to be all the way down at 0.5 amps. So that sort of begins to explain how these things are linked. But wait, there's more. You don't just have to rely on, you don't have to just rely on voltage. You could change other things. Let's say that let's say that this time let's keep our resistance constant. Let's say that your let's say in this case your resistance is, let's pick a number, let's go with 8. Let's say your resistance is 8 ohms. Okay, we'll take our formula V equals IR, and let's say that we and so therefore let's say our voltage is 2 volts. That means that our resistance is, our current is going to be oopsies, let's say our voltage is 8 volts, then our current is going to be 1 amp. Yep. So what? Let's say now that our resistance is still, you know what? This is actually really difficult to do. Let's change this formula. Let's change this formula to be R equals V divided by I. That's going to be a lot easier to work with. Let's now use that. We've got 8 ohms. And let's say that we've got, let's use the same example that we did before. We've got, if we've got 8 volts, then that means we're going to have 1 amp. Okay, cool. What if we've got more than that? What if we've got 16 volts? Well, if we had 16 volts, then to get to 8, we would have 2 amps. You double the voltage, so you double the current. Let's do one more. Let's go 8 volts, 8 ohms, sorry. And what we'll do is we'll go with, if you're going to, by the way, draw the ohm symbol, you just sort of draw like a pimple looking thing. Let's go with 24 volts. We have 24 volts, then we're going to need 3 amps. Well, it's going to push through with 3 amps. And again, this makes sense. If you give your electrons more and more push, if you increase the slope of your mountain, then your flow down the river is going to go from slow to really, really, really fast. And that's the same thing. If you give your electrons more push, then you can, if you give them more push, then you can make them move faster, as long as the resistance stays the same. And we could do the same steps if we looked at the current. We could look at keeping the current at 1 amp. And if the current's at 1 amp, if you increase the voltage, then the only way to, if you decrease the voltage, the only way to keep the current the same is to decrease the resistance. Sometimes you want to make sure that you don't put too much current through a wire. So sometimes you have to increase the resistance if you've got to increase voltage. But these are how all these things are linked. Let's actually do an example, and then that'll be the end of the lesson, because I'm looking at the time now. It is 11:45. We're almost at the end of the lesson. So let's do an example here on this. A torch uses a 9-volt battery and 100 milliamps of current through the circuit when the torch is on. How much resistance is in the lamp of the torch? Well, let's jot down our information. We've got 9 volts, so V equals 9. We've got 100 milliamps, so I equals 100 milliamps, which is the same as 0.1 amps. Now, how did I do that? Because a milliamp means it's a thousandth of an amp. So all I did was I just took 100 divided by 1,000. That gives me 0.1. So if I know that V equals IR, and if I want to calculate R, all I can do that is just divide both sides by I. That will give me R by itself. So V divided by I equals R. I know what V is. V is 9 volts. I know what I is 0.1. So 9 divided by 0.1 gives me 90 ohms. In, around, across. And that's how we can calculate the resistance of a circuit using Ohm's law. And we're going to do a fair bit of this, because I would like to get you guys to build up some practice in dealing with Ohm's law. And this is pretty much what Electronics 1 is going to be all about, is getting you guys some practice with Ohm's law. But I'm going to talk to you guys about that tomorrow. So Thursday's lesson, that's what we're going to be doing. It's got one section here which is called current and charge calculations. Whoopsies. And what they do is we've got a bunch of questions about just current and charge, and just calculating if you've got this much current and this much charge. There's a bit of an example at the top. Let's have a look at that example actually. Let's explore it. The example for an unknown quantity. If I have 0.26 amps and 500 coulombs, then what time? I want to know what the time is. So how do you find that out? You take I equals Q over T. That was one of the formulas that we started off with. Current equals the charge moving in a certain amount of time. How many electrons there are, and that's how we get the charge. We rearrange that, so we get T equals Q over I. You can think about that as just swapping the T and the I. You can actually do that with any sort of formula where it's something divided by something. And then once you've swapped it, you just put in the values of Q, which was 500 coulombs, the values of I, which is 0.26, shove them in. That gives you 2.1 times 10 to the power of 3, and the units in this case are seconds. So in this particular page, there are, in this particular page, we've got a couple of basic, super easy questions. Be careful. the answer needs to be given in minutes, in seconds. But I've given you these ones in minutes. And then at the bottom, we've got some worded ones. But the worded ones shouldn't still be too difficult. They should be just the same as these ones above, but they're using words. Underneath that, we've got some Ohm's law practice. And it's just 2 pages. And there are these questions here. You can print this off or you can do this online, up to you. Let's go have a look at this example here. A 9-volt battery. A 9-volt battery is connected to a toy bird, and the current through the speaker is 1.5 amps. What is the resistance? Well, again, we've got V equals IR, but we want R. So we're gonna have to rearrange this. We're gonna have to divide both sides by I, V equals IR. If I divide both sides by I, there's me V over I equals R. Then once I've got that, I can substitute 9 and 1.5 in. And then once I do that, that gives me I, which comes out to be 6 ohms. Sorry, I got that wrong. Which comes out to be 6 ohms. And so then that's what you would write down. A quick point here, I wanted to show you guys, you know what, I might show you here. Now, you don't actually need to know this, but if you are really bad at rearranging your formulas, if you go V equals IR and you can't jump, if you can't jump to I equals V over R easily, then you might want to think about, and especially if you're really bad at rearranging, you might want to think about using this. It's called the pyramid method. And you might have seen this with the I equals PRT over 100. You can do the same thing with simple interest using this formula, but I like it for V equals IR. What you do is you write V, I, and R in this order. And how it works is that if you want to calculate I, what you do is you cover up the I, and that tells you I equals VR. VR. Job done. Let's just say you want to calculate. Let's say you want to calculate R. So what you do is you cover up the R, and R equals, it's got V and I've got an I, VI. And if I want to calculate V, which is the easiest one, it's still important to do. What you would do is you would cover up the V. You've just got I and R left. So V equals I, R. But the I and R are next to each other, whereas these other ones are on top of each other. It's a quick and easy way that it's called the pyramid method. It works for a lot of equations, but if you're really bad at rearranging, then I would suggest you would do it. Before I let you guys go to start working on that, I will quickly show you guys. Yeah, so this is the lessons that we're working on here. We're doing the 2 Ohm's law things here. We're doing this one and this one together. I'm not going to go through this lesson. I think sometimes we go through that lesson. I thought, you know what, I'm just going to give you the whole lesson to work on it. What I will quickly say is what we did in class last lessons, we added in resistance. So if you missed last class, you missed out on this learning of resistance. Resistance is measured in ohms. And what we do with ohms is it gives us an understanding of resistance, or how difficult it is for the energy to flow. If something is able to flow really easily, we say that we can actually use resistors as components. And so if you put a resistor in, it makes it harder to flow, which means that lights will become dimmer. We said that a material with high resistance is called an insulator, like wood, air, and plastic. An area with low resistance, which allows all the electrons to move super easily, is something like copper, gold, water. These are all great values of something called conductors that allow
Hello.
to go through. Yo. Okay. We then combine these ideas. We said that, and I spent a lot of time talking about this. I said that current is the flow of water like down a river. I said that voltage is the push that pushes that water down the river. And of course, the resistance are the rocks and twigs and sticks and stuff in the river that get in the way. And that's sort of one of our issues. Okay, so and then we moved on to talking about vehicles IR. I said that vehicles IR is a formula that can be used to explain that as your voltage, the push down the river gets increases, your flow down the river, your current also increases because you can move down that river faster. If your resistance increases, but you've got the same push down the river, then your current, the flow of the water will go down. Same as in electricity. Your resistance goes up, your flow through that circuit is going to go down. If your voltage goes up, your flow through that circuit is going to go up. And if you want to have a really, really, really fast flow through the circuit, if you want I to be really, really, really big, then you need to make sure that your voltage is really, really big, or your resistance is very small. You barely have anything in the way. There's two ways that you can explore that. And then what we did was we did a quick calculation.
I just got it.
I didn't actually show you that. I'm sure showing you that I didn't. I ran out of time. I'm not going to show you now because I might show you later, but yeah, I might show you next week. But then we did some examples with Ohm's law, and we quickly did some Ohm's law practice and stuff like that. There is one thing I wanted to show you guys with regard to that just before I let you go, which is I'm quickly going to share which slide am I going to share? This one here, this one here. Let's do this. Let's see if I can find this super quickly. V equals IR FET. Let me see if I can find this. Ohm's law FET. Is this perfect? This is exactly what I was looking for. This is sort of the same idea here. So if I want to get a really high, as I said to you guys just 2 seconds ago, if I want to make sure my current is really, really large, I can do that in two ways. I can do that by increasing the voltage. That's one way to make I really large. And that means that you're going to get more push through the circuit. Or instead, we could decrease the resistance, make it super easy. Make it super easy for the electrons to go through the circuit. And you could do both. You could do that and you could do that. And that would just make the current go really, really large. And so this is a nice little animation to show you how these two things are linked. If you have a very, very low voltage and you have a very, very high resistance, makes it really hard for the electrons to move through. Guess what? Your current is going to be minuscule, very, very, very small. So that's just a cute little animation that I like to show people sometimes. And he's playing the alien shit. It's actually part of the app. So it's a very annoying sound, but they think it adds to it. Yeah, trust me, it's not one of you guys. I'd be yelling if it was one of you guys that are like, guys, we're trying to learn here and you're playing this annoying music. Yeah. All right. So